Well, here we are, almost at the end of June term, and we have 3 more sections that we will be covering in Chapter 4. The section today, or the first section for today at least, does not delve that much into probability. It's a bit of a detour so that in the next section, we can connect these topics to probability calculations again. But in section 4.5, we are specifically focusing on counting techniques. Now, don't groan. I know you know how to count to 10 or 100 or 1,000 if you had to, but we are going to look at specific applications of counting here, counting how many ways certain actions are possible. For example, the New York Lotto game is a lottery that consists of you picking 6 numbers ranging from 1 through 59. And you win the lottery if your 6 numbers come up in the drawing. And so you may want to know, well, how many possible outcomes are there? Let's say you just want to be the eager beaver and you want to buy every possible lottery ticket combination. How many lottery tickets would you have to buy? Well, there is a little more than 45 million different lotto outcomes. So that's how many tickets you would have to buy. And this also means, since there is only one winning combination, the chance or the probability of you winning that specific lottery is 1 in about 45 million. Now here, it is not practical to try and list out every single lottery combination, right? Conceivably, you could do it with a computer, but usually the goal is not to list out every possibility. The goal is to understand how many possibilities there are. And so we're going to look at formulas that help us with counting in situations such as this one. And let's look just at a basic example to illustrate the concept here. Let's say you are doing an experiment that consists of 2 actions. Your first action is flipping a coin, and your second action is drawing a number between 1 and 3. And I want to know how many outcomes are there to this experiment. Well, we can easily draw a tree for each of the actions. So when you start the game, you flip a coin, and so the first branching of this tree consists of the 2 possible outcomes from the coin toss, heads or tails. Now, after this, whether you see heads or tails, the next thing you're going to do is draw a random number. And there are 3 possibilities here. So if you draw heads, there are 3 possibilities that could follow. And if you draw tails, there are 3 possibilities that could follow. And so in total, this tree ends up having 6 branches, each one corresponding to a different outcome of the experiment. Now, on this tree diagram, each time a branch splits, it's because an action is being performed, and the number of splits corresponds to how many possible outcomes are there for that specific action. So each branching represents a different action, and after each action, you then have potentially multiple branchings, like the coin toss splits heads, tails, but then for each of those outcomes, we need 3 new branches to represent the drawing of the random number. So you could imagine that these trees could get large pretty quickly. The idea that we see in this tree, though, is if we just know how many outcomes each action has, then we can use a bit of multiplication. So flipping the coin, that has 2 possible outcomes, and there are 3 possible outcomes for drawing a number between 1 and 3. And so if we just multiply those, the 2 outcomes on the first action multiplied by the 3 outcomes on the second action gives us 6 total outcomes for the experiment. And this is something we can now generalize to something known as the basic counting law. And the basic counting law says, if you are performing 2 actions, the first one can be done in a number big M ways, and after completing that task, the second action can be completed in big N ways. Then in total, there are M times N possible ways for those 2 tasks to be performed together. So in this case, 2 outcomes corresponding to a coin toss multiplied by 3 outcomes corresponding to the drawing of that random number. And so 2 times 3 is 6 possible ways to perform the experiment. And this can easily be extended to multiple tasks. For example, if you had a third action and it could be performed in O possible ways, then it would be M times N times O, the total number of ways to perform the experiment. M times N times O possible outcomes for the experiment. And you can keep going with the multiplication. In fact, let's look at an example here. Suppose you have to set up a password for your bank account, and you are told your password must consist of 4 letters followed by 2 digits. So if we visualize this, if we, slide jumped all the way to the end. Let me just back up here. So if we think about this password, there will be 4 letters, and then there will be 2 numbers, right? It'll be 4 letters first, followed by 2 numbers. And we want to know how many passwords are possible if any letters and digits are allowed. Now, let's just assume this bank is based in the US, and so we are working with the standard alphabet, right? And so how many letters are there in the alphabet? Well, there are 26 letters. And how many digits are there if we're choosing a number? Well, it could be 0 through 9. So there are 10 possible digits. So first thing you're going to do is pick a letter. How many ways could you pick that first letter? 26 ways. Now you're picking a second letter. How many ways could that be done? 26 ways again. 26 options for your third letter and 26 options for your fourth letter. And each time we can multiply them together, right? We are ultimately performing 6 different actions here. First, picking 4 letters, and repetition is allowed. And then we're picking 2 digits, and repetition is allowed. So for the digits or the numbers, 10 possibilities and another 10 possibilities. And the basic counting law says we count how many ways it's possible to perform each individual action, and then to find the number of possibilities for the whole, we just multiply those together. So the number of passwords in this case, well, 26 is repeated 4 times and 10 is repeated twice. So 26 to the power 4 times 10 squared, and that gives us 45,697,600 passwords. So a really almost close to 45.5 million passwords here. What if the bank modified things a little bit? They said, oh, you're setting up this password in the same way, 4 letters followed by 2 digits, but no repetition is allowed. So let's just visualize this for ourselves again. So we'll have letters first, and then we'll have numbers. So when you pick the first letter, you have 26 possibilities. But now, since no repetition is allowed, once you've made that first selection, that one letter of the alphabet is no longer available to you. So how many options do you have when you're picking the second letter? 25 options. Now you've used up 2 of the alphabet letters. So how many possibilities do you have for the third choice? That would be 24, and then 23 for the last one. Now you get to numbers. When you pick the first number or digit, you still have 10 possibilities, but now you've used up one of them. It's not available to be selected again, and so there are 9 options after that. So in this case, the number of passwords, since they don't allow repetition, is 26 times 25 times 24 times 23 times 10 times 9. And that gives us 32,292,000. So we've gone from more than 45 million to only around 32 million by imposing this restriction that you cannot reuse letters. So in some sense, it's more secure. Well, it is more secure if you allow repetition of letters, in the sense that there are more potential passwords, right? If someone is trying to guess a password to hack into your account, there are an extra 12 million passwords they have to consider. The downside here is sometimes when people know they're allowed repetition, they'll do a password that's just the letter M 4 times, M, and then the number 2 twice, 2, 2. And hackers sometimes know that people gravitate towards specific patterns. So that's why you sometimes have these password restrictions that try to avoid passwords that have a patterned nature to them, like saying, oh, no repetition of characters is allowed. Now, there are 2 very specific counting techniques that will be important for us going forward. The first of these is known as a permutation. Now, a permutation is an ordering of groups or objects. For example, say I have 3 objects. I have a blue triangle, I have a green star, and I have a red heart. And I want to line them up in a specific order. So if you look at the illustration here, I could line them up. First the triangle, then the star, then the heart. Or I could line them up first the star, then the heart, then the triangle. Each of those is a unique permutation. And many counting problems involve permutations where you're interested in figuring out in how many different ways can you line things up. For example, connecting back to our chapter on voting, we could ask how many different election outcomes are possible. How many lineups are there for a first choice, and then a second choice, and then a third choice, and then a fourth choice if there are 4 candidates. Well, this is an example of a permutation, lining up the candidates from your first choice to your last choice. So permutations can connect back to voting, for example, if you are asked to rank your candidates. So there's an example where you line election candidates up in a specific order, and each such order is called a permutation. So how do we calculate the total number of permutations that are possible? Say that we start off with little n objects, and we're going to place them in a line. So we want to know in how many ways can we line them up. Well, when you place the first object, you have n choices, right? Any of your n objects could be placed first. After placing that object now, when you go to place the second one, you don't have all the objects anymore. You've placed one of them already. So there are n-1 choices for the second place. And then when you place the third one, there are n-2 choices for the third place. And you keep on going in this way until you get to the last place and there's only one choice left for the last place. So by the basic multiplication rule, we can now find the number of permutations by just multiplying the number of options we had for each position in our lineup. So n times n-1 times n-2 all the way to 1. That's the total number of permutations. And we sometimes call this n factorial, and it's denoted by n exclamation point. If you see an n with an exclamation point, it means take all the integers from 1 through n and multiply them together. Let's just take a look at a quick few examples of that. Say I ask you to calculate 4 factorial. That would mean 4 times 3 times 2 times 1, and if you multiply this together, it's 24. Or if I ask you for 7 factorial, it would be 7 times 6 times 5 times 4 times 3 times 2 times 1. And so now you can see the multiplication can get tedious pretty quickly. But if we do this multiplication here, we get 5,040. Now, there is a factorial button on your calculator, and during our next Zoom session, we'll make sure everyone knows where to find that and is comfortable using that. Just 2 technical things to show you. 1 factorial means all the integers starting at 1 and ending at 1. So 1 factorial is equal to 1. And a number that sometimes comes up in calculations is 0 factorial. Now, you can't start at 1 and then multiply increasing integers all the way to 0. So by definition, we say 0 factorial is also equal to 1. And that kind of makes sense because in how many ways can you arrange 0 objects? There's only one arrangement. You're not placing any objects down. That's the only arrangement that's possible. So one possible arrangement of 0 objects. So what would a permutation problem look like? Well, say you have 12 DVDs, and I know people don't even really have DVDs anymore, but let's say you still have 12 DVDs nicely sealed in their cases. You're a collector of some sort, and you want to line them up on a shelf. In how many ways could you do this? Well, this would be if you line them up, you know, first place, second place on your shelf, third place, all the way to in the 12th place, there would be 12 ways, 12 choices when you place the first DVD, 11 when you place the next one, 10 when you place the next one, and finally when you have just one left, there's only one placement you can make. This is the same as 12 factorial. And this is now where it's really handy if you know how to do the factorial on your calculator without having to multiply all those integers. And in this case, it gives us 479 million and some change. So if you just have 12 DVDs, there is more than 479 million ways in which you could arrange them on a shelf. Of course, not all permutation problems involve lining up all n objects. For example, think of an election, right? Maybe in an election, I don't care about how you rank all 10 candidates running in a race. I only care about how you line up your top 3 choices. So I want to say, oh, there are 20 candidates. in how many ways could people create a top 3 list ranking first, second, and third place. So we don't care about all n objects. We only care about how a smaller subset of them, which we denote by little r, how we could arrange those. This we call a permutation of n objects taken r at a time. And the notation for this number is a subscript n for the total number of objects, a capital P for permutation, and then a subscript r again. So the first number tells us the total number of objects, that's the n, and the second subscript number, the r, tells us how many of them we're actually interested in. And the basic idea is the same. You ask yourself, how many options are there for my first choice? N. Now you take away one of the options, so how many options are there for my second choice? N minus 1. And you keep going. You start with n, and you multiply the next r minus 1 integers less than n. So you keep going to the integer equal to n minus, in parentheses, r minus 1. What's really useful to know is this can be done with direct multiplication, or it can be done using factorials. The number of permutations of n objects taken r at a time is equal to n factorial divided by n minus r factorial. And the only thing to be careful of here is noting that n minus r factorial is not the same as n factorial minus r factorial. These are two very different numbers. So you want to do the subtraction in the parentheses first before applying the factorial. And if we ask ourselves, what happens here if we are not interested in just r objects, we are interested in all n of them, well, n permutation n ends up being equal to n factorial, which is what we would want. So watch that a second time, like rewind on this video a little bit if that sounded like a lot of gobbledygook, but here is how an example would play out. A club has 92 members. The club has to select a president and a vice president. In how many ways can they do that? Well, how many choices are there for president? 92 possible choices. Since the same person cannot be president and vice president, after selecting the president, there are 91 choices left for vice president. And so if we are choosing 2 people out of 92, and you want to know how many choices of 2 people are possible, the answer would be 8,372. Now, note, if I'd applied my rule here, if I'd said 92 permutation 2, my rule would have said, okay, 92 factorial divided by 92 minus 2 factorial. So this is 92 factorial divided by 90 factorial. And things can actually simplify a little bit here. Remember, 92 factorial means it's all the numbers 1 through 92 multiplied. But that means I can always take 92 factorial and write it as 92 times 91 times 90 factorial, because 90 factorial is still all the numbers 1 through 90, and I'm dividing by 90 factorial, and very conveniently, I have some cancellation here. So again, I'm left with 92 times 91, and that is equal to 8,372. And I will again show you tomorrow, but there is a button on your calculator that will do the permutation for you directly. You input the n, you input the r, and it calculates it for you. You do not have to do manipulation of the numbers here. There's one other counting technique that's important, and that is combinations. Sometimes we don't care about the order in which objects are selected. We only care about which objects are selected and in how many ways that could be done. And this is where the lottery is important. Ding, 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 if you are thinking about the project you're working on. A lottery is a system where you don't care in which order the numbers get drawn. You know, if you have the number 3 and the number 57 on your lottery ticket, you don't care which one of those gets drawn first. You only care about which numbers ultimately get drawn. So if we're looking at a group of objects where the order is irrelevant, we call that a combination. And the notation we use for that most of the time is subscript N, capital C, subscript R, so comparable to the permutation notation, just a C for combination now. But sometimes people will use parentheses and write the two numbers one on top of the other, almost like a fraction, except there's no horizontal line indicating a fraction. It's just one number on top of the other. And that we sometimes read as N choose R. So in how many ways can we choose R objects out of a set of N? And there's a connection between combinations and permutations. You can always find the number of combinations by taking the number of permutations and dividing by R factorial. Or we can go and write all of this in terms of factorial. The number of combinations can be written as N factorial over R factorial times N minus R factorial. But again, there is a combination button on your calculator which streamlines this a whole lot. But let's take a look at two quick examples. Let's stick with the lottery example. You're playing the New York Lotto. You have to choose 6 numbers out of the set 1 through 59. So how many possibilities are there for you to choose from? There are 59 possibilities. And how many are you going to choose? 6. So in how many ways can this be done? Well, this would be a combination because we don't care about the order. And so you can go and do this, you know, the brute force way using the formulas, or if you just enter this on your calculator, which we'll go through tomorrow, then this is the number we saw earlier. There are a little bit more than 45 million options here. Okay, now, last example for this video. Suppose that there are 15 entries in an art contest. There will be several prizes awarded. There'll be a first, second, and third place. And then after that, there will be 4 honorable mentions. In how many ways can these awards be made? Well, there are 2 pieces to this problem, right? We have to award a first, a second, and a third prize. And that's something where order is explicitly important. And then we have to award 4 honorable mentions. And here the ordering is not important. It's not like it's 4th place, 5th place. No, we're just saying these other 4 people, they did really well. So here are 2 actions, right? Our law of multiplication says if we can count how many ways to award the first 3 places, and we can then count how many ways to award the honorable mentions, then we know how to do this. We just multiply those together. Now for the first 3 places, order is important. So that would be a permutation. Out of the 15 people, we want to know in how many ways can we choose 3 top finishers. And how many people are now left that are eligible to be the honorable mentions? 3 of the 15 people are out of the running now. There are 12 people left, and we're choosing 4 of them. So the first part, first, second, and third place, order is explicitly important. And thereafter, for the last 4 honorable mentions, order is not important. But we have to calculate each of these individually. So there's 2,730 ways to award the first 3 prizes, and then there are 495 ways to award the honorable mentions, meaning the total number of ways in which prizes could be awarded is equal to 1,351,350. But the important takeaway here, we had 3 rules in this section. Basic multiplication, which says if you're doing multiple actions and you can count in how many ways each of them takes place, you can just multiply things together. If you're counting how many arrangements of objects are possible, that's a permutation, so order important on permutations. And finally, if you're just counting how many selections are possible and order is not important, that's a combination. We will definitely do several more examples of each of these during our next Zoom session.